Thrusting space science into the audio dimension. This is Naked Astronomy.
Hello, welcome to the third of this week's special episodes of Naked Astronomy, brought to you from the National Astronomy Meeting, organised by the Royal Astronomical Society in St Andrews. I'm Dominic Ford, and in today's podcast, we travel to the end of the world to find out what the last life forms on Earth might look like. I catch up with some of the amateur astronomers who are here at NAM, and why might future robotic explorers of the moon find themselves engulfed in dust? As always, if you'd like to get in touch, tweet at Naked Scientists or drop us an email to astronomy@thenakedscientists.com.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientists.com/astronomy.
Over periods of hundreds of millions of years, the light of the sun is gradually increasing as its supply of fuel, hydrogen gas, diminishes. In around 5 billion years, it will become a huge red giant star and will completely engulf the Earth. But much sooner than that, its growing warmth is likely to drastically change the environment of the Earth. What kinds of life might we expect to find at the end of the world? Jack O'Malley-James is from the University of St Andrews.
As the sun ages, it sort of starts burning through its reserve of fuel, and as that happens, the sort of core of the sun contracts, and because it gets contracted, it heats up more and the reaction speeds up, and so the net result is you get a more luminous star, a hotter and brighter sun, and then this has knock-on effects for the planets orbiting it, including our planet. So the Earth is going to heat up as the sun throws out more energy towards it, so surface temperatures start increasing. So over the next billion years or so, you're going up in luminosity by about 0.1 of the current value. But then once we get to the end of that billion years, we get to a tipping point where rapid ocean evaporation sets in. And because water vapor is a greenhouse gas, this sets in motion a runaway greenhouse effect. And then temperatures really rapidly start climbing, the oceans really start evaporating, and over a further billion years from that, we lose all the water vapor from the atmosphere to space, and then we're left with a very dry planet.
So how do you go about modelling the effect that an increase in the sun's luminosity has on the climate of the Earth?
So because of the timescales that we're looking at, it almost doesn't pay to have a very complex model in place. So we have a very simple surface temperature climate model, which takes into account greenhouse gas values and the changing luminosity of the sun. So it puts all these together and calculates the temperature at different points over the surface of the Earth, so different points in latitude, and just gives a rough idea of temperatures or average temperatures in these particular zones. And then we sort of extrapolate that upwards as well and work out the temperature profile upwards in the atmosphere, which gives us an idea of temperature change with altitude as well. And then we can start using those temperatures to work out when we start losing liquid water in certain habitats and what kind of microbes could and could not live there.
Now, I know you've been researching what impact that will have on the sorts of life forms we see on Earth. Are we going to go back to an era like when the dinosaurs were around, when the Earth is a warmer place with more cold-blooded creatures, do you think?
Something like that is possible within the very early stages, before we get this rapid ocean evaporation taking place. So the other effects in terms of life that's coming into play is the increase in silicate weathering. So if you have more water vapor in the atmosphere, you have more rain, and rain draws down carbon dioxide from the atmosphere when it interacts with silicate rocks and minerals in the surface. And so if you've got more rain, you're taking away more carbon dioxide. Take away carbon dioxide, it's not really a good situation for plants. So once we start lowering carbon dioxide levels, plants start to die off, and the animals that depend on the plants also start dying off. And the most vulnerable animals are also the ones that have most recently evolved. So the larger mammals and things like that will be probably the first to go. And so colder-blooded reptiles would have a better chance of surviving for a little bit longer. But it's a very short window of time. So plants and animals would all be on a rapid decline into extinction.
So if you lose the plants and you lose the animals, does that mean you're just left with bacteria and fungi?
Yes, you'd end up with, at first, probably a fairly diverse microbial world. similar to the early Earth in a way. So the early Earth was solely inhabited by microbes for a good couple of billion years, and it would be a return to that. But then, because conditions become more extreme, temperatures increase, only the really hardy extremophile microbes will be the ones that can really survive. And there's likely there'll be similarities between these and the sort of extremophiles we see on Earth today in places like Yellowstone and other sort of volcanic springs and things like that. But it's also thought that these were the very first life forms to evolve. So the early Earth was a very hot, hostile environment, and so it's thought that when life first emerged, it emerged to fit these conditions. So these kind of microbes were possibly the first microbes on Earth, and it's possible they'll be the last as well.
I guess the search for life on Mars has, in recent years, become focused on what might be beneath its surface, where it's thought there might be a more protected environment. Would a similar thing happen on the Earth, that if the sun was getting warmer, then life might thrive better beneath the surface?
It's definitely possible. Because we lose the plants and we lose oxygen, we also lose ozone, which forms a protective layer around the atmosphere that sort of protects life from UV radiation. So you'd expect to see a movement underground just for extra UV protection. The situation gets a bit complicated because the general trend, if you were to look at the temperature profile of the crust of the Earth, as you go deeper down, temperature goes up. So if you've got very hot temperatures on the surface, you'd get very hot temperatures underground as well. And so that if it's too hot for life on the surface, it'll be too hot beneath the ground. But this is just a general trend. And you see on Earth today, I think the deepest they've found life is something like 5 kilometers down. And it depends on the particular rock type. So it's very hard to put a final lifetime on life underground to the point where life could actually have its final refuge underground.
Historically, our ideas about where life could thrive haven't been terribly accurate because nobody predicted the existence of extremophiles, for example, in very hot, very acidic conditions. Do you worry about the fact that we're trying to think about how life might adapt to extreme environments when everything that we see is evolved for the Earth as it is at the moment?
One of the constraints with this work is that we're limited to what we know about life at the moment. And it seems like every year there's a new microbe that's discovered that pushes the extreme of something like temperature even further than we thought. So it's very difficult, given the time periods that we're looking at, to rule out the possibility of life evolving over 1 billion years to then suit the conditions as they change. But it's not something that we can predict, so we're just very limited by the information that we have at the moment.
But I guess it's very timely because we're discovering large numbers of extrasolar planets, and it's very interesting to think about whether those might have life on them.
Yeah, so this is one of the reasons we started doing this work, is because if you were to look at an Earth-like planet, so imagine an exact copy of the Earth around another star, and we were to take a snapshot of this in time, either in its early lifetime when life first started or in the far future when the conditions are not very good for quite a lot of life, you're more likely to come across microbial life on the surface than you are the sort of rich, diverse biosphere that we've got today. So it's very useful to have an idea of what kind of telltale signatures this sort of microbial world would leave behind that's different to the signatures that we'd see from life as we know it on Earth today. So it sort of helps in the search for life in different scenarios.
Thanks, Drac. That was Dr. Drac O'Malley-James from the University of St Andrews. The National Astronomy Meeting is primarily a conference for the UK's professional astronomers. But it also encompasses the work of amateur astronomers too, and each year a few of the country's most dedicated amateur observers come along. Tom Bowles, who lives in darkest Suffolk, has the remarkable distinction of having personally discovered more supernovae than any other individual in history. He's also one of the British Astronomical Association's vice presidents.
Well, the aims of the BAA is really to promote serious observing amongst amateur astronomers, both within this country and internationally. It's really quite a large organisation worldwide now.
How many amateur observers are there in the UK?
Well, there are 3,000 of them are part of the BAA, but I would imagine that amateur observers is probably run into the tens of thousands if you take everybody who observes, whether it's seriously or just for fun.
And when you say serious observing, some of the most serious observers can actually contribute scientifically useful observations.
Oh, very much so. I mean, some of the historic observations that go back over the last 2 or 3 centuries have all come from amateurs. I mean, when I define a serious observer, I really mean somebody who just writes down what he sees and records it and hopefully passes it on to somebody else so that it can be recorded for history.
Now, we're also joined by Paul Sutherland here from the Society for Popular Astronomy. Paul, what's the aims of the SPA?
Well, the SPA has been around for 60 years. We're celebrating our Diamond Jubilee this year. We were set up by amateurs, including Patrick Moore, who felt that there was a need for a society to help young people or people at a popular level to get into astronomy. And we've been basically doing that for 60 years, training people up.
And I guess that really helped engage a much wider audience into astronomy.
Well, we hope so. We hope to show that astronomy is fun. You know, you don't have to be very serious about it. You can just observe with the naked eye alone, for example. Plenty to see, plenty to do.
Tom, I guess your work really demonstrates that serious observing can contribute a vast amount to science because you've discovered more supernovae than any other person in history.
I don't know if that should be a scientific challenge or not. I think some of it's down to sort of sheer stubbornness and sort of just repeating, doing the same thing all the time. Yes, I've discovered 152 supernovae to date, and I hope that some of those have been used to somebody at some time. I know it's certainly generated a lot of papers. A couple of them I've co-authored myself. But yeah, they have been used to perhaps calibrate bigger surveys and, more important, work further along the field. So I hope I've made a contribution.
How do you go about hunting for supernovae?
Well, you just keep looking. You just take hundreds and thousands of pictures and you compare those with archived images that you have on your hard drive of your computer, and you just do it over and over and over again. Yeah, it sounds boring, but it isn't, because obviously, you know, every galaxy is different and the shape of every galaxy is unique. And when you see the same old friends coming around year after year after year, it does stimulate you, and that's partly where the motivation comes from. If it was only discoveries that motivated you, you'd give up very, very quickly. You'd just get bored. I guess it takes me roughly 4,000 images for every discovery I make, so that works about 120 hours work at the computer with the telescopes to get one discovery. So consider the number of clear nights we get in the UK, that wouldn't last very long.
So are you working down a list of nearby galaxies which are close enough that a supernova in those galaxies would be bright enough for you to see?
Yes, that's basically the idea. Although I don't differentiate between, say, Type 1 and Type 2s. Type 1As I can see a bit further away than the Type 2s because they're optically brighter. But at the end of the day, I just go out for as far as I hope to see supernova and galaxies. And at the moment, I've got just over 12,000 galaxies on my list. So over the period of 12 months, I get round the whole sky, and I just keep imaging the same galaxies over and over again until, you know, I get a result.
And I guess you have turned this into quite an industry. Is it 3 telescopes you've got?
I've got 3 telescopes, yeah, and I run sort of typically 60-second integrations using rather sophisticated CCDs. I use back-illuminated cool CCDs now, so I've got sort of research-grade cameras. And I get about 135 images an hour, so if I start building those up over the winter months, that leaves you with several thousand images to check over a night. So actually taking the images is the easy bit. Checking them and eliminating them for supernova suspects is the hard bit.
I'd imagine that must drive you insane, looking at these thousands of images trying to find supernova candidates.
Well, that's the fun bit, isn't it? I mean, there's no point in taking the image if you don't look at them. And you sort of, I'll tell you what's really funny. I've been doing it now for 15, 16 years, and I can actually spot proper motions in some of the images, you know, between the archive images I've got and the fresh images I've taken in any night. You know, if you look at it, and the unsuspecting eye might think you've discovered an asteroid in there, but it's actually a star that's jumped across there about half an hour a minute. And it's quite motivation to see how the sky changes over a very long period as well.
So these galaxies really are becoming old friends for you. But I gather you've had a few difficulties in the last few years. Your observatory was struck by lightning a couple of years ago.
Oh yes, that was 5 or 6 years ago. And it happened during the day. Nothing was switched on. All the telescopes were disconnected, the PCs were disconnected, but everything came up over the communication earth lines and just did thousands of pounds worth of damage. And that put me down for about 6 months, but I've recovered from that now. It's going well now.
Your plan to keep up this work, or is the competition from surveys like Pan-STARRS starting to become too much?
Well, it's not so much Pan-STARRS, but, you know, they put this big CCD camera on the Schmidt telescope, the 40-inch Schmidt, and that is really cleaning up the skies quite well. So, yeah, the big surveys are becoming a big challenge. I've still got the edge, I think, because I'm perhaps a little bit more flexible in them and I can move around the sky a lot easier. How long that'll last for, I don't know. But I'll keep doing it until the results dry up. But it's getting tougher.
Yeah, I was just going to say that Tom is a remarkable example of an amateur doing amazing things, which not long ago were really in the professional domain. It's partly because there's fantastic equipment now available to amateurs at more reasonable prices. But most of all, it's down to his dedication. Not everybody can be a Tom Bowles, but young people joining the SPA, for example, they can use less equipment or even just their eyes. We can help to teach them some of the techniques that they can go on and discover supernovae for themselves eventually if they want to.
I guess it is quite incredible that the equipment available to amateurs can't be more than about 10, 20 years behind what professionals have access to.
This is absolutely true. If you look at some modern imaging of galaxies or planet Jupiter, for example, using CCD cameras and software techniques for working on those images, they rival or they're better than images taken by professional observatories just 30 or 40 years ago. It is quite remarkable. It's been a revolution in amateur astronomy.
And if people are keen to get involved, where can they find out more?
Well, the easiest way is if you go to the SPA website, which is at popastro.com, and you can find, it's a busy website, there's a nice forum there that people can join in with, and you'll learn all about how to join and what we do. For example, we provide 6 magazines a year and newsletters and things, and a lot to do, a lot of fun.
And Tom, if there are amateurs who are wanting to do serious scientific observation, where can they find out about the BAA?
Similarly, on the BAA website, it's britastro.org. And they go on there, they'll find the names of the sections, the different observance sections, and a list of the meetings that we hold. And why not just pop along to one of the meetings and introduce yourself? We'd be pleased to see you there.
That was world record holding supernova hunter Tom Bowles from the British Astronomical Association. And we were also joined by Paul Sutherland from the Society for Popular Astronomy. Tom isn't the only BAA member here at NAM this week. Lee MacDonald is keenly involved in the association's solar section, and earlier in the week he gave a talk about how to observe the sun.
Solar observing can be an expensive hobby, but it doesn't have to be. You can observe the sun in ordinary visible light with a small telescope, like a 60mm refractor, and simply projecting the sun's image onto a piece of white paper or card. The important thing to remember always about the sun is that it's potentially extremely dangerous to look at, so you should never look at it directly through a telescope of any kind, because you will damage your eyes, and you can't assume that a filter that makes the sun look dark actually is safe to look through, because much of what the sun emits is actually in infrared, and that's, you can't see it, but it's still cooking your eyeball, essentially. So if you do use a filter, only use one that goes over the front of a telescope, and that is actually designed for solar observing with a telescope that is known to be safe. And amateur astronomy societies will be able to advise you on what filters to use.
And I guess that warning also goes whenever you're pointing a telescope anywhere close to the sun in the sky.
Yes, that's right. I mean, for example, if you're looking at Venus in daylight or something, make sure the sun is hidden behind a solid building. Otherwise, if the sun comes accidentally into the field of view, that could have disastrous results.
Now, I think amateur observations of the sun can actually be quite scientifically valuable. We've heard a lot in the last couple of days at NAM about professional observations of the sun. What can amateurs contribute?
Well, the best thing that amateurs can do with observing the sun is measure solar activity simply by counting the number of sunspots and spots and groups seen. The global industry standard for solar activity is called the relative sunspot number, which takes into account the number of groups of sunspots that you see and also the number of individual spots within the groups.
So if you project an image of the sun onto a piece of paper, you're counting the number of dark splodges you see on that image of the sun?
Yep, that's essentially what you're doing. You're counting the number of dark splodges. And the more people who do this, the better the statistical average we get, and so the more accurate picture of the sun's activity we get. And astronomers have been doing this, measuring solar activity by this method since 1848. So we now have a huge, very long set of very consistent data, which tells us what the sun is doing in the long term, with obvious implications for things like climate and so on as well.
I guess as compared to other areas of amateur astronomy, observing the sun is rather easier in that you don't have to do it at the dead of night.
Mm-hmm. That's correct, yes. You're not out in the cold, antisocial hours, especially at this time of year. It's quite nice to observe the sun when you get home after work, and you can also show other people the sun, and that's what makes it good for bringing astronomy to a wider audience as well, is the fact that they can observe it, during the daytime. They don't have to come out during the night when it's cold and dark.
There were a lot of spacecraft with cameras looking at the sun, and we heard earlier in the week about cameras on rockets even. How can amateur observations compete with that?
Well, they don't really compete with that. They rather complement it. Basically, no one's going to launch $1 billion spacecraft to count sunspots, so that's left to observers on the ground. And some professional observatories do sunspot counting, but the largest sort of body of physical numbers of people doing it are actually amateurs. Most professional observatories are imaging or observing the sun in exotic wavelengths, many of them not visible at ground level, such as X-rays, which is just as well because they'll kill us all if the X-rays reach the ground. And so we amateurs are observing the sun in a different light, as it were.
And I guess the continuity you got back to the 19th century is also helping you to compare past activity with current trends.
Yes, absolutely. We can compare how active the sun was, 100, 150 years ago with what it is now, for example. And we find the recent solar maximum has not been as active as some people have predicted. But it's not actually unprecedented. There was, at the early years of the 20th century, in the 1900s, there were long periods of many months when there weren't any sunspots. So we can see this is not the sun switching off or anything like that. It's not, the sun does this every so often, where it's slightly less active than it should be.
Given the sun has been quite quiet in the last solar cycle, does that make it more boring as an amateur to observe the sun?
Yes, it can do, especially when it was at solar minimum back a few years ago, when there were periods of about 2 or 3 months sometimes when there weren't any spots on the sun. But now we are at maximum, and although the sun is not as active as we would like, there's usually something to see on the sun each day.
And I guess part of the fun of it is that you never quite know what the sun's going to do next.
Absolutely, yes. From one day to the next, the sun's never the same, and it's not predictable. It's not like eclipses or the phases of the moon, things like that. It's absolutely, you never know what sunspots are going to appear, suddenly disappear. Sometimes sunspot groups grow very, very suddenly. And that's part of the fun of solar observing. You never know quite what to expect.
How many observers are there in the BAA who are regularly taking observations of the sun?
About 60 to 70 observers. It depends slightly on the time of year when people are active and so on. But yes, it's about that number regularly send in sunspot data to the BAA solar section.
So that's quite a fantastic data set you're collecting there. It must mean that most clear days you've got information on what the sun's doing.
That's right, and indeed some of our observers, they live in all parts of the world, sometimes in the southern hemisphere as well. So for many years now, I think the BAA has managed to have at least one solar observation on every day of the year in the records.
My thanks to Lee MacDonald from the British Astronomical Association's solar section. The Moon's closeness to the Earth makes it an ideal place for testing new technologies before sending them to more distant parts of the solar system. But even though several robotic rovers have been sent to Mars, none have yet explored the Moon's surface. This is about to change as space agencies around the world seek to learn more about our nearest celestial neighbour. Farida Honoré from Lancaster University warns that the dust on the Moon could be quite a hazard for any rovers for descent there.
There are at least 7 international missions which are planned to go to the Moon from now. August 2013 is the first one, and there are a lot more in plan for 2020, including the manned mission.
So obviously the Moon is the only body that we've ever sent astronauts to. What scientifically can these rovers do that the astronauts in the 60s and 70s couldn't do?
Well, rovers, they used vehicles in the era of Apollo's because they give them the mobility to go around the surface and to collect information and data rather than the humans. If they want to walk on foot, they won't get that far.
And I guess the Moon is also a fantastic place for testing new technologies because it's so close and easy to get to.
Exactly, and the mission which is planned for 2018, which is known as International lunar network by USA and other international collaborators. It's actually planned for testing communication technologies. They're planning to put the stations in different places and be able to see how communications work in the lunar. And that is one technology to be tested at least.
Now, I know in particular you've been thinking about the dust on the moon's surface. What problems could that cause for rovers?
It can stick to, because the dust can be very sticky, it can also penetrate. If it has got iron molecules, which some dust do, then it can actually be very toxic. So there is hazards in terms of damage to elements of the vehicles and erosion. It also affects the visibility for any landing on the moon, because the dust can levitate and can something in the atmosphere, which will be difficult. In fact, I think in some of the missions they had this difficulty is knowing exactly where they're landing.
I think you've been particularly worried about what might happen to the dust grains at sunrise and sunset on the moon.
Yes, the terminator region in the moon is an interesting from the scientific point of view, because on one side of it, the moon surface gets charged to a positive value, and the other side, which is the night side, it gets charged to a negative value. So there is a big potential difference, and that can produce a large electrostatic force which can levitate the dust. And that is, I think, the region which is probably more problematic in terms of if you're landing around that region.
So on the Earth, I guess it's quite common that when you've got a piece of plastic or something that gets electrostatically charged, dust tends to stick to it. Is this the same problem that these rovers would encounter?
Well, we have to include the cohesion force, which is an important one, and it affects different size particles in a different way. So if you include that in the simulation, what we have shown is that it will actually limit the range of the particles that they can be lifted. And that's something that has to be taken into account when you do the simulation to get the correct result.
So are there ways we can mitigate these hazards in the design of rovers we're sending to the moon?
Yeah, there is a lot of work going on that at the moment, especially in the States, from what I know. There's big laboratories just to do different type of study in terms of engineering and mitigation, as you said, to get ready for the missions.
Am I right in thinking the first of these rovers is actually going to land very soon, next month?
Yes, it's called LADEE. It's an orbiter and is by US and is designed to study dust in detail. So that information would be very useful. We have some information from the dust that was gathered from the Apollo missions, the things that actually came back, and from the study people have done on the spacesuit of the astronauts to get the dust by the tape sort of thing and then produce the dust distribution. We have information about the dust formation and the dust distribution, but what we don't have is the dust profile. And you just have to guess how that works.
And are you just modelling this to mitigate the risks this dust might pose, or is it actually telling us something interesting about the formation of the moon itself?
It's more in terms of the plasma physics, to be honest, because once dust gets charged, it behaves like any other plasma. So from my perspective, it's the understanding of how a complex plasma works when you have both the electrons, ions, then the normal plasma, and the dust, charged dust. And that can be not just on the surface of the moon, it will happen all the other places where the dust is dominant. It also works in the laboratory, for example, for this sort of jet repulsion, the column sort of things and the studies that they do. A lot of the time they do produce dust and they want to get rid of it, and they want to see how that can affect the reading and information.
So this is actually incredibly multidisciplinary. This dust is helping you to understand how ionised gas behaves as well.
Yes, that is correct. I think that is the most important aspect. It's the science part of it, that it's not just for designing, or because I'm not an engineer, I'm not studying to understand just the medication of the dust, but understanding how the dust behaves in a collective behaviour within the plasma.
The moon isn't the only dusty body in the solar system. Mars, for example, sometimes has these huge dust storms. Can these same techniques be applied elsewhere in the solar system?
Yes, dust is everywhere, and that is what is interesting. But in each environment, you have to look at the local conditions. For example, on Mars, you have an atmosphere which in some ways mitigates the effect of the dust, because the dust can then combine with the neutral atmosphere in that, the charged part. But, for example, the things that I'm interested to study next would be the dust on asteroids, because they behave very much like the moon's surface, but because they don't have the same gravity, there will be a limited range of the size of the dust that could actually be staying on the surface of the asteroid. Anything small dust, they would sort of levitate soon, and they won't be sort of sticking to the surface. So it would be interesting to see what, for a given asteroid, what kind of condition that will have in terms of its environment with the coverage of the dust.
My thanks to Professor Farida Honoré from Lancaster University. That's all for today's Naked Astronomy, but don't forget that you can find more episodes of the podcast at thenakedscientist.com/astronomy. Tomorrow I'll be exploring the dark universe to find out about the latest models of dark matter. I'll also be hearing from two researchers who claim that it's possible to construct cosmological models that don't include any dark matter in the conventional sense. If you'd like to get in touch in the meantime, you can send a tweet at Naked Scientists or email astronomy@thenakedscientist.com. Naked Astronomy is produced by me, Dominic Ford, and comes to you from Cambridge University, with support from the Royal Astronomical Society and the Science and Technology Facilities Council.